In this video, we'll take a look at categorizing collisions into types. Two main categories are elastic and inelastic, and there's a special case of inelastic called perfectly inelastic. We'll talk through those and identifying them and how you can do calculations with those. The questions we're going to be asking to tell the different types apart are, is momentum conserved and is kinetic energy conserved? Again, if something is conserved, it means the amount you have at the start is equal to the amount you have at the end, that we haven't created or destroyed any or transformed it into other types. Whatever we have at the start is equal to whatever at the end. So the first type, elastic, a collision that is inelastic. The answers to the questions are, so that's the categorization. You say, now, momentum is conserved. You say, well, in order for that to be true, we recognize this equation as being the change of momentum is equal to the impulse, the force times the duration of the force. And you say, really what we're doing here to find the total change of momentum, we got to add up all of the impulses, all the forces through time. Well, if the forces all balance out, and so your total force, outside force is zero, then your delta P will be zero. And if that's the case, the momentum isn't changing. So the momentum I have at the start equals momentum at the end, the momentum is conserved. And for a system like that, you could add up all the momenta of all the pieces before and set that equal to the sum of the momenta of all the pieces afterwards. And so you could write an equation like this. In this equation, we could add up the momenta of all the parts, mv plus mv equals mv plus mv. The second part is momentum conserved. You say for an inelastic collision, you can do the same thing. Where the two types of collision are different from each other is in the answer to the question, is kinetic energy conserved? Now, we're not asking, is energy conserved? For that one, we'd be looking at the equation. In this equation, this is the work done, which is when a force acts through a distance. So we're adding up all the forces through distance, F delta X's. And again, if all the forces are balanced out, then your total work done is going to be zero. And then the kinetic energy at the start equals kinetic energy at the end, which would let you write the following equation. Adding up all the kinetic energies, the 1/2 mv squared plus 1/2 mv squared of all the parts before. If I had more than two parts, I'd have more than two terms, equals all the kinetic energies of all the pieces afterwards. So we're just putting in the final velocities instead of initial velocities there. As that gives you another equation you can use to help solve. But for an inelastic collision, you can't write this equation. The kinetic energy is not conserved. And you say, well, why might the kinetic energy not be conserved? Well, because there's some outside force doing work, or because some energy is being transformed into other forms. For example, if I take a ball and I drop it onto the tabletop, and it's going to repeatedly bounce, it's not going to bounce as high each time because some of the energy is going into other forms. When it hits in that collision, some of the energy goes into vibrations, and so energy is seeping out into other forms. And so my kinetic energy of all the objects afterwards are not equal to the kinetic energy of the objects before, and so I can't write this equation. So examples of these, you say, well, when you think about it, when I have collisions, am I usually going to have collisions that are elastic or collisions that are inelastic? What's usually going to be the case? You say, well, isn't it true that whenever things collide, aren't the atoms, there's going to be some vibration and some shaking and the atom's going to wiggle and jiggle and you're going to generate thermal energy? Isn't that going to be the case? Some of the energy gets transformed into thermal every time you have a collision? You say, well, so aren't collisions generally going to be inelastic? So when would I have a collision that is elastic then? Well, the example that we oftentimes see, you'd say, well, to have something that's elastic, where no energy goes into vibration or wiggles and jiggles, you couldn't have an internal structure. If I have an internal structure, right, the bits are going to get squished and move apart from each other. If I had fundamental particles, like talking about protons and quarks and leptons colliding, you say, well, then those guys, right, are little fundamental particles. You could say, well, gosh, they don't really have an internal structure to wiggle and jiggle, right? Those quarks and leptons. So then you say, well, gosh, then I could imagine that collisions between those would be elastic. And you say, on the one hand, isn't it true that everything in the universe is made up of these fundamental particles that don't have internal structures. And then they say, so on the teeny tiny level, if you could add up, the kinetic energies of each individual particle, right? You know what I mean? Then those collisions would always be elastic. Okay, sure, but no one wants to have to keep track of the motions of every little individual particle and add up all the kinetic energies. When we look at bulk materials, though, you're going to have an internal structure, and you're going to have wiggling and jiggling and vibration, and some energy is going to go into thermal every time. But so you say when we say elastic, we're talking about fundamental particles, those smallest particles of nature that we're aware of. They don't have an internal structure to get crushed or stretched to wiggle and jiggle. And so we could say that no energy goes into thermal in those collisions. But what we'll do is we'll approximate. We'll say, well, gosh, what if my object was really rigid? Okay. And so when it collides with things, it doesn't wiggle. The particles can't wiggle and jiggle very much. It's a really pretty stiff, rigid object. Then we could say, well, gosh, so little energy goes into wiggles and jiggles. We'll say close enough we can approximate it as being elastic. The classic example of this that we use is a lot of times they talk about the balls on a pool table, on a billiard table, right? And you're going to like shoot on a pool table. We say that oftentimes we'll say that the pool balls, usually we call those billiard balls. We can approximate it as being elastic. Now, is it really? You say, well, no, and you can tell because in a collision there's a sound, right, of those balls hitting, right, and that you're making that sound by vibrations, right, by wiggles and jiggles. So obviously, right, that collision is not truly elastic, but we can approximate that way and say, we'll say it's small enough amount when to other forms, we'll just ignore it. Inelastic, then you say that's pretty much every other collision pretty much is going to be inelastic. Pretty much everything other than that. The other thing we'll sometimes do is if I have objects that interact electrically or magnetically, and so they don't actually come in, right, and they kind of repel each other away, right? So they're coming in and they interact and come apart. That's a collision, even though they don't actually physically touch. And in those collisions, you can have it be pretty darn elastic, right? And so we could probably approximate those as elastic. But otherwise, pretty much all collisions on the large scale are going to be inelastic. Now, there is one more thing that I should show you, and this is a special case of inelastic. So what is a perfectly or completely or totally inelastic collision? It's a collision where the objects hit and stick together afterwards. So you might imagine having some squishy little car, and some great big car comes in and hits it, and they move together afterwards. Okay, and so in the case where they hit and stick, or we'll sometimes talk about like in football, maybe someone's making a tackle and they one guy's running and the other guy comes running, oof, and they move off together afterwards. You say that's a completely or totally or perfectly inelastic collision. And so what this is just physics slang for objects move together after the collision. Now, because this is a type of inelastic collision, momentum is conserved. And because this is a type of inelastic collision, kinetic energy is not conserved. So anytime you see a collision like this where they hit and stick and move off together afterwards, you automatically know kinetic energy is not going to be conserved. Now, why this type is cool is because when we write the equation, because they move together after the collision, these two final velocities are the same. So we can write the equation if we wanted as afterwards, those two v's are the same. So they would like factor out, we could factor them out, and I could write it as ma plus mb times that common final velocity. That says ma plus mb times v final. Gosh, that's really sloppy. But that's the way we can write it. So what this means for us, it means the following. When we're using these to solve now, take a look at this equation. How many different variables are in this equation? And you'll say, well, gosh, there's 6 variables in that equation. There's the mass of A, the mass of B, the velocity of A before, the velocity of B before, the velocity of A after, the velocity of B after. That's 6 different variables, right? And so you say, but over here, how many variables are in this equation? You say, well, 6 variables, and it's the same 6 variables. Now, if I only had one equation, they give me 6, they'd have to tell me 5 of them so I could solve for the 6th, right? But now, because I have 2 equations to work with, they only have to tell me 4 of the variables, and I can write 2 equations and substitute and solve. And so what that means is they only have to tell me 4 instead of 5 variables. If I know that it's elastic, it's like that gives me another piece of information. It lets me use this formula, so it makes it so that I can solve that other way. On the other hand, if a collision is inelastic, then you say, well, gosh, there's 6 variables. They would have to give me 5 out of the 6 to solve, unless it happens to be perfectly inelastic. Then I only have 5 variables because there's only one final velocity instead of 2. So now they only have to tell me 4 variables and I can solve for the 5th. So that's kind of the deal. So something to be aware of is that when they tell you something is perfectly inelastic, they're giving you another piece of information, making it so there's one less variable, one less unknown to deal with.